we're going to talk about properties and changes. We're going to talk about physical and chemical properties, physical and chemical changes. Physical properties first. Definition here, physical properties can be observed without changing the substance's chemical makeup. So what I mean by that is if you are observing water, H2O, all these observations that you can take, all these properties that you're going to take note of, you're not going to change water into anything else other than H2O. So the formula remains the same. The chemical makeup remains the same. Examples of physical properties are viscosity, conductivity, malleability, hardness, color, odor, density, melting point, boiling point. Another thing with physical properties is the amount of substance is not going to affect any of these properties. Okay? No matter if I have a small cup of water or a large tub of water, the boiling point is still 100 degrees. And that's something that students may need convincing of because when they think of boiling, they a lot of times think of time. And so they'll think, well, you know, a small amount of water is going to boil faster, which is true, it does, but it still boils at the same temperature as a large pot of water, and that's what boiling point means. Density is another one, and we have a whole lesson about density that we'll talk about. So those are some properties. Just a reminder, viscosity is resistance to flow, so something is very viscous and it's really thick. Conductivity, ability to conduct electricity. Malleability, that'd be able to pound a substance into a sheet. Ductility, I don't have up here, but that's pulling into a wire. The rest of them, I think, are self-explanatory. Why do we need physical properties? We can use physical properties to identify materials and to choose materials. So that's one of the standards for ninth grade is kind of, you know, what type of physical properties make this a good material. So that's something that we can talk about there. On the flip side of that would be, or the opposite, would be chemical properties. Chemical properties can be observed only by changing the substance's chemical makeup. So once you observe a chemical property, you've changed that substance into something else. Examples are flammability. So if you set something on fire, you're going to be producing different substances than what you started with. Reactivity, obviously, as that implies, you're going to be reacting substances and producing new things. So I think properties are pretty easy for students to understand, but where we get into some difficulty is when we start talking about physical and chemical changes. And so I just want to take a minute to review our 3 levels of chemical representation. We talked about this a little bit when we talked about matter and the classification of matter. So remember, symbolic, we're talking chemical symbols and mathematical equations. Particulate, we're talking about at the molecular level. We have to use models to get at this. And then macroscopic, that's your lab work, what you can actually see. And so the way I like to present this to my students is I use something from Target Inquiry, and they have these really great pictures, models. The activity is called Change You Can Believe In, and the website is here, is gvsu.edu/Target Inquiry. These resources are free to educators. I actually print out the cards for my students. They're all colored like this, and I laminate them so I can use them from year to year. I pass the cards out, and they have to decide, you know, what kind of change do you think this is? And they have to be able to justify why they think so. And so here's the first card that they would look at. You can see 3 black circles, a red, lots of whites, and here's a red and 2 whites. And when you come over here, a lot of times when students immediately look at this, because it's so jumbled, they think, oh, it's chemical, it's chemical. But when they look closer, they can see 3 blacks, lots of white, a red. It's exactly the same. Okay? Red, 2 whites, red, 2 whites, exactly the same. So no chemical makeup has changed here. And so most of my students, of course, at a high school level, get to where that this is a physical change. We haven't changed our chemical makeup. The next card you'd look at is this one. And about these cards, we do another segment where we actually do the macroscopic level here. of some of these. We definitely do this one at the macroscopic level for you in the video. And so students here, they can see it's definitely a bit of change, chemical change. You got the gray circle to the gray circle with the plus, two reds together. The reds are no longer together. You've got this negative sign in there now. So most students pick that out as chemical. This one you can see that same, nothing's changed here. We've just bent it, so physical. This one, they can see a change here with your gray circles, and now over here they're not all together anymore. Now there's a positive. Here you've got some whites with pluses, and the whites with pluses are not over here anymore, and now there's two whites together. A lot of times when students first look at this, they don't really know how to read this one because this is the first card in the series that's got 4 different circles. And so what you've got is this and this come together to form these two things. And my students and I talk about, well, why did they have to show this and this separate from one another? So we talk about phases a little bit. If you look here, these two whites together, they're all very, very far apart. And so I say, well, what kind of phase do you think this is? What's a gas? And so I say, well, if you're actually in the lab doing this, what's your gas going to do? And they will tell me, to bubble out. And I say, so that's why they had to show it separate from this, which is more like a liquid, and in this case, a mixture, a solution. So when you do this activity, you can really pull back in, and you should pull back in the whole classification of matter as well. Maybe even have them start with that. What is this? Is this an element? Is it a compound, a mixture? That's a nice place to review there. This one the students have a hard time with because it does look pretty similar, and it's really hard. They have to look at these really closely, and they'll be able to see red and 2 whites. And a lot of students at the high school level go ahead and deduce that this is water, and a lot of your middle school students probably will too. 2 reds together here, and when you come over, we have a lot of differences going on. Orange with no charge, now the orange does have a charge. Reds, no charge, and now we do have reds with charge. And so most of them pick that out as being chemical. This one, red 2 whites, they pick that out as being physical. This one is the hardest one. And this is the one where we really can get into a bit of a debate. And there's even a debate in the scientific community about this example here. But at the high school level, at the middle school level, we want them to think of this as being physical change. So we have red 2 whites, yellow positive. There hasn't been a change there. Green negative. There's really no change. This is broken apart, but it hasn't changed into something new. And that's something we got to get out. Now, I'm going to go ahead and talk about this one because it's the one with the discrepancy. This is actually water and salt. And so, when you put salt and water, you get a solution. And that's what this is representing here. The neat thing and where the discrepancy comes in about dissolving salts, and not just table salt, okay? But when you dissolve some salts, you get an energy absorption, you can get an energy release, and that type of activity is usually reserved for a chemical change. Also, you get a change in physical property here. Solid salt will not conduct electricity. Salt in water definitely does conduct electricity. So usually when you get a change in physical property, that's indicative of a chemical change. So there's actually some debate in the chemical community about the dissolving of salts or ionic substances as being chemical or physical. So you can talk about that with your students. I think it's kind of interesting. You can find some resources for them to read about it. But for the test that they have to take, dissolving is a physical process. And when you look at this, there's been no change chemically. Nothing is different. It's just split apart. So this is a good place to kind of introduce some argumentation in science with supporting their decision. My high school students, I have them kind of split to either side based on chemical or physical and then defend their answer. And most of them are pretty well one side or the other in high school, but this one really kind of gets them, and it's a good one to put in because of that. This is the very last one, I think. And so here you can see black, 3 reds, and a white. And here we have a black and 2 reds. And again, this is that situation where a gas is forming, so they have to show it separate. And this is a chemical change. So when we finish the card activity with my students, I'll have them write down, what do you think is a chemical change? What are ways we know a chemical change has occurred? And in high school, they immediately start telling me stuff like color change, heat release, gas formation, stuff like that. So they kind of go back to what they have been taught in previous years. Whereas we've spent all this time looking at these cards at the particulate level. And so when I start hearing things like that, what I'll do is I'll say, oh, color change, that means chemical change. And I have my food coloring there, my water. And I say, oh, the water is clear. I put in my food coloring, it's red. Does that mean a chemical change has occurred? And they kind of pause for a minute. Okay. And I say, oh, gas formation. Here's my water I have on my hot plate. I see lots of gas formation. And so they kind of gives them some pause. And so what I really want to get them to, and what we do eventually get them to, is that the best way to look at whether it's been a chemical or physical change is at the particulate level. Because there's no discrepancy there. If the molecular structure changes, is different, then a chemical change has to have occurred. Whereas all these observations, these macroscopic observations, can sometimes be misleading. And so what you want to get them to at the end is that a chemical change is when the chemical makeup has changed. A physical change is when the chemical makeup has not changed. And the only way we can really look at that and really be sure is by looking at the particulate level or by looking at the symbolic level when you actually start writing the chemical reactions. For example, this is one that we do show the macroscopic of it in one of the next videos. I want to talk about this one. So if you look here, this is actually representing magnesium. And when you go to the Target Inquiry website, they will have an atom key that goes along with this that you should not give your students at first. And so based on our atom key, this is magnesium. And so at the symbolic level, we would write Mg with an S because it's a solid. This is oxygen. And remember we talked about diatomic elements. You put a G there because it's a gas. And what forms then is magnesium oxide. And so if you think way back to our discussion of writing formulas, Mg and O, they come together, metal, non-metal, so it's going to be ionic. And so we can write our correct formula by thinking of our charges. Mg is +2, oxygen is -2. And so how many of each do you need to make it equal 0? You need 1 of each. And so the correct formula for our product is MgO. Okay? And we can look at the way these ions are arranged, and we know that this is a solid. And so at the particulate level, you can see that a chemical change has occurred. Mg is no longer by itself. O2, there's no longer 2 together. It's changed into something different. At the symbolic level, you can see this as well. And at the macroscopic level, it's pretty obvious too, and you'll see that in later videos. Just a little quick note, you should notice that we're not balanced right now. We've got to have conservation of matter, and we can do that. We've got 1 magnesium here, 1 here, so that's good. 2 oxygens, 1 oxygen, so that's not good. We add a coefficient to balance that out, and we have to add another one here. Okay, and so I just want to kind of pull the particulate piece and the symbolic piece together here. So for this one, a physical change, 1 red, 2 whites, that's H2O. In this drawing, the molecules are close together, liquid, but not in a rigid structure, so liquid. Over here, same thing, 1 red, 2 whites, so H2O. Very far apart molecules, so gas. And so what this represents is boiling. We do have gas formation when you have boiling, right? It's just the same substance. And so this is balanced, and this represents a physical change. because we haven't had a change in our chemical makeup. So physical changes, just to recap, chemical makeup's not changed. Examples are changing phase and dissolving. And chemical changes, the chemical makeup is changed, and this is the key, okay? Here's some examples that sometimes happen, not all the time, okay? It occurs when a substance reacts and forms a different substance. So again, lots of chemical changes don't do any of these, okay? Hydrochloric acid with sodium hydroxide, acid what's a base, none of these things happen, but it's still a chemical change. And so you want to really kind of pull away from this type of wording and this type of focus to this focus. Look at your particulate level or your symbolic level as well. But these are some indicators that a chemical change has occurred. Change in color, production of a gas, formation of precipitate. Okay.